Hello, this talk is going to focus on understanding acid-base physiology from a practical perspective and look at the interpretation of a variety of parameters that are presented to us on a blood gas. So I've put a couple of multiple choice questions together to kind of facilitate the discussion. And the first one is, with respect to blood gas interpretation A, pH represents the log to the base 10 of the hydrogen ion concentration. B, the blood gas analyzer measures pH, PCO2 and bicarbonate. C, pH may relate to the Henderson-Hasselbalch equation as follows, and you can see the equation there. And D, bicarbonate is most indicative of a metabolic disorder or compensation. As we go through this talk, try and commit yourself to an answer. Even if you're wrong, you're more likely to remember why you're wrong and perhaps what the right answer was if you do make a decision. So first of all, we'll look at the definition of pH. pH is by definition the negative log to the base 10 of the hydrogen ion concentration. And an abnormal pH then is either defined as an acidemia, where pH is less than 7.36, or an alkalemia, where the pH is more than 7.44. So option A had pH as the log to base 10 of the hydrogen ion concentration and is incorrect because the negative sign was not included. Now the blood gas analyzer measures only two variables from an acid-base perspective. Obviously a blood gas analyzer can measure other metabolic parameters like glucose, lactate. It measures the partial pressure of oxygen, etc. But from an acid-base perspective, the blood gas analyzer measures only the pH and the PCO2. And all of the other variables are calculated, including bicarbonate and the various derivatives thereof. In terms of the Henderson-Hasselbalch equation, we understand the basic equation that pH is equal to the pKa plus the log of base over acid. And if we translate this into our bicarbonate system, then pH is pKa plus log of the bicarb concentration over carbonic acid concentration. And if we apply this then to the bicarb system, then pH is equal to 6.1 plus log of the bicarb concentration divided by the PCO2 multiplied by its solubility coefficient. If we have a look at this equation, then we can express it in two ways. And in the top panel there, you can see that I've put 0.03 times the partial pressure of carbon dioxide, whereas in the bottom one it's 0.225 times the partial pressure of carbon dioxide. And the reason for this difference in the solubility coefficients relates to the units in which the partial pressure of carbon dioxide is measured. So for the top equation, the PCO2 is measured in millimeters of mercury, and for the bottom one, the PCO2 is measured in kilopascals. And so if we look at question 1 then, the correct answer was C, where pH is equal to 6.1 plus the log of the bicarb concentration divided by 0.225 times the PCO2. And that would be correct if the PCO2 were measured in kilopascals. Question 2. So a patient in recovery room following a maxillofacial procedure is noted to have a degree of airway obstruction. And in terms of this clinical scenario, all I want to emphasize is that this is a patient who has an acute airway obstruction. And blood gas analysis reveals the following. So the pH is 7.2, the PCO2 is elevated, it's 8.3 kilopascals, and the bicarbonate is 27. So which of the following is correct? This represents a partially compensated respiratory acidosis. The elevated bicarbonate indicates early renal compensation. C, the base excess would be approximately +3. And D, the elevation of bicarbonate is a result of the increase in CO2. So if we look at the equation for the hydration of carbon dioxide, if carbon dioxide dissolves in water, it produces carbonic acid, H2CO3, and carbonic acid can dissociate into hydrogen ions and bicarb ions. And in fact, physiologically, we make use of an enzyme to facilitate this process to allow for the transport of CO2 in a more efficient manner. But it's important to appreciate that from this equation, if CO2 increases, which we see on the left-hand side there, then so does the hydrogen ion concentration. And so any acute increase in CO2 will produce a concomitant acidosis because of the production of hydrogen ions. But it's very important to see in this equation that for every hydrogen ion that's produced, there's also a bicarbonate ion produced. And so when carbonic acid dissociates into hydrogen ions and bicarb ions, we get a bicarb produced for every hydrogen ion. And this obviously has nothing to do with compensation. This is just simply a chemical fact. And so if we dissolve carbon dioxide in a glass of water, then we can alter the pH of that glass of water through the production of carbonic acid, and that glass of water will then have a lower pH because the hydrogen ions, but will also demonstrate an increase in bicarbonate, which obviously has nothing to do with compensation. So it's also important to appreciate that as far as bicarbonate goes, any change in the pH and or the PCO2 will affect this variable. And we cannot then use the bicarbonate to distinguish between respiratory abnormalities from an acid-base perspective or metabolic abnormalities from an acid-base perspective. And I think this is the one point at which a lot of people get themselves into trouble and confusion by trying to make inferences about metabolic disorders by looking at the bicarbonate. So this value from the is produced by the analyzer, and it's useful to the blood gas analyzer, but it's not really particularly helpful to us from a clinical perspective. Another variable that's produced is the standard bicarbonate, and here the blood gas analyzer will remove all the abnormality that is present in the PCO2 and then recalculate what the bicarbonate would be, and it assumes then that the PCO2 is 5.3 kilopascals, which is the midpoint of normal. And it also assumes the temperature is 37 and that the hemoglobin is fully saturated. And this is a useful number to us. And it identifies metabolic abnormality specifically. Remember, I said that when the blood gas analyzer calculates the standard bicarbonate, it removes any abnormality that was present in the partial pressure of carbon dioxide. And it can then identify metabolic abnormalities either as primary problems, primary metabolic acidoses or alkaloses, or if there's a change in the values because of a compensation, perhaps from a renal perspective. And then the last two that I want to focus on is, first of all, the base excess. So this is defined as the amount of acid or alkali required to return the pH to normal for plasma in vitro under standard conditions, and it really amounts to the difference between the standard bicarbonate and normal. And if we think about this, a normal standard bicarbonate would be 24, and if the standard bicarbonate is 24, then the base excess is 0. If the standard bicarbonate is 30, then the base excess is 6. And if the standard bicarbonate would to be 18, then the base excess would be minus 6. And I think that's relatively straightforward and self-explanatory. And then the last variable is the standard base excess, which is much the same in concept as the base excess, but the calculation will assume anemic blood with a hemoglobin, an average hemoglobin of 5. And what the blood gas analyzer is trying to do here is give us a representation of what's happening in the extracellular fluid. So clearly hemoglobin is present in the intravascular space, but if we look at the extracellular fluid, that would encompass the plasma that's present in the intravascular space and the interstitial fluid. And if we were to take the hemoglobin concentration which is present in the intravascular space but average it over the whole of that extracellular fluid, then the average hemoglobin would be lower. And if you want to use, if you want to engage in therapy or adjustment of the pH through the administration of bicarb, then this is potentially the number that should be used for therapy. And by definition then, the standard base excess is the amount of acid or alkali required to return the pH to normal for plasma in vivo. And in the clinical arena, it's probably the best measure of metabolic disturbance. So in terms of question 2 then, looking at the right answer, the correct answer here is that the elevation of bicarbonate is quite simply the result of the increase in CO2 from that equation that demonstrated the hydration of CO2. The third question, also a little clinical scenario. So a patient with long-standing obstructive airways disease presents for an elective hip replacement, and the blood gas is as follows. So the pH is 7.33, the PCO2 is 8.3 kilopascals, the bicarbonate is 32, and the standard bicarb is 30. So which of the following is correct? A, the changes in base excess mirror changes in PCO2 in respiratory problems. In other words, they move in the same direction. B, the fact that the standard bicarb is lower than the bicarb is evidence of compensation. C, the base excess should be about 12. And D, this is a fully compensated respiratory acidosis. So first of all, a few words on compensation, and that's just to say that this is really never complete. But we have to think about what we mean when we use the word complete. And clearly, we could interpret complete to mean that the process has come to the furthest point that is physiologically possible. In other words, in its completeness, there is no more potential for compensation. Or we could interpret complete as the compensation returns the acid-base status back to normal. And when I say this is never complete, that's what I mean there. Obviously, the compensation process could come to its completion in terms of the fullness of time, but we can never compensate ourselves back into a normal range. So a small abnormality of pH will always remain. In other words, the pH will fall outside of that range of normal of 7.36 to 7.44. We can't compensate ourselves back into the normal range. And when we see a pH which is within the normal range, and we can identify acid-base disturbances, then we're usually dealing with more than one acid-base disturbance working against one another to bring the pH back into that normal range. So the pH disturbance that is present on the blood gas will always echo whatever the major abnormality is in terms of that pH upset. So as far as compensation goes, in reality, compensation can be about a half way back to normal, and at best up to about 3/5 of expected. So if we look at metabolic acidosis, for which we can compensate the best in terms of hyperventilation, we can manage to compensate our pH about 3/5 of the way back to normal. So I'm now going to give you some basic rules of thumb which are very useful in the clinical arena, and for those of you who criticize this approach, you are welcome to go and look at all the equations for the calculation of compensation. There's a different equation for each acid-base disturbance, but I often find that these simple rules of thumb are far more useful in the clinical environment and when you're looking at acid-base disturbances in the clinical arena. So if we look at the interaction of partial pressure of carbon dioxide and base excess on pH, a 0.1 unit change in pH, so that would be, for example, from 7.4 to 7.3 or from 7 to 7.1, would require a change in partial pressure of carbon dioxide of 12 millimeters of mercury or 1.6 kilopascals, and a change in base excess or standard bicarbonate of 6 milliequivalents per liter. So to go through this then in more detail, as I've already said, a 0.1 unit change in pH would be created if we have a change in CO2 of 1.6 kilopascals or a change in base excess of 6 millimoles per liter, or a mixture of the two. And so to give you some examples then, a pH of 7.2 could be caused by a PCO2 of 8.5 kilopascals. In other words, it's gone up twice 1.6 kilopascals, but there's no change in the base excess or the standard bicarb at all. In other words, a pure respiratory acidosis. Or the CO2 could have gone up to 6.9 kilopascals, in other words, by 1.6 kilopascals, and the base excess has dropped by 6 milliequivalents per liter. So we're picking up 0.1 unit change in pH from the PCO2 and 0.1 unit change from the change in the base excess. Or we could have a PCO2 that's plumb normal at 5.3 kilopascals, but a base excess of minus 12. So this would be a pure metabolic acidosis. Or a CO2 of 3.7 kilopascals with a base excess of minus 18. In other words, the base excess of minus 18 would drop the pH by 0.3 units, so from 7.4 to 7.1, but the lowering of the PCO2 by 1.6 kilopascals pushes that pH up again by 0.1 unit to get to 7.2. And so if we understand these rules of thumb and we are able to apply them, then we can predict what should be happening and look at blood gas values with a certain amount of insight into what should be happening. So in terms of the patient that we presented here, the pH was so if we look then at question 3, the correct answer was that this is a fully compensated respiratory acidosis. In other words, an acidosis in which compensation has achieved the maximum that it's ever likely to achieve. Moving on to question 4, a known insulin-dependent diabetic is admitted after developing a soft tissue infection. The patient has been taking aspirin at home for analgesia. And if we look at the blood gas now, it looks as follows. So the patient has a pH of 7.2. The CO2 is 3.8 kilopascals. The bicarb is 10 and the base excess is minus 18. So clearly when we look at this just from those values, this patient has a metabolic acidosis as the predominant disturbance, and there's also a lowering of the CO2, which could perhaps be part of compensation, or there's another process driving it. So which of the following is correct? The low base excess is evidence of a ketoacidosis. The acidemia indicates a lack of compensation. The strong iron difference will be low. Or were full compensation to occur, the pH would be about 7.38. So if we start to look at metabolic acidosis first of all, this is a common primary problem. So we encounter metabolic acidosis very frequently in the clinical environment, and a reduction in base excess is far less seldom, far more seldom part of compensation. So if we have to deal with metabolic acidosis, we should approach it systematically, and the traditional teaching is to use the anion gap, but we can also use strong iron difference and have a look at the total amount of weak non-volatile acids, so ATOT. If we look at the anion gap first of all, we calculate the anion gap by looking at the difference between sodium and potassium, from which we subtract the sum of chloride and bicarbonate. And we can then classify anion gap based acidoses into those raised anion gap acidoses, which are usually from things like elevation of lactate, ketones, or in the setting of chronic renal failure, also rhabdomyolysis, and then there are a couple of drugs and poisons which can create the problem, and those are very typically the organic compounds, ethanol, methanol, ethylene glycol, etc., and then some specific drugs, particularly the salicylates, metformin, and INH. Now, as far as anion gap goes, we can also have normal anion gap acidoses. And from a traditional teaching perspective, the typical causes of a normal anion gap acidosis are long-standing diarrhea, ureteric diversions, and pancreatic fistulae. And from a drug point of view, we see normal anion gap acidoses from acetazolamide overdose, also some of the bile sequestrants and ingestion of ammonium chloride. Now, the difficulty with anion gap as a tool to explain acidosis is we end up with an acidosis when the anion gap is both raised and it's normal, and that clearly indicates that in that anion gap we don't get an insight or an understanding of what causes the acidosis, and so we have to have that kind of rote learning approach to knowing what the causes of a raised and a normal anion gap acidosis are. If we switch to looking at strong ion difference now, the strong ion difference is the difference between all the strong cations, sodium, potassium, calcium, and magnesium, and the strong anions, chloride, and any other strong anions that may be present. And if we just start off looking at this equation and we think about how much these variables can shift within the realms of physiologic plausibility, we don't encounter abnormalities of magnesium where the magnesium changes by tens of millimoles per liter. Similarly, calcium, the same thing. So calcium and magnesium, from a physiologic perspective, change by a relatively small numeric amount within the realms of physiologic plausibility. Potassium can shift more, but if we think of what the lowest potassium and the highest potassium we've ever seen in a living patient, we're probably talking about a shift of potassium of less than 10 millimoles from the lowest to the highest. Whereas if we look at sodium and from an anion perspective chloride, then we really are aware that sodium and chloride can shift by a relatively huge amount. And so when we look at strong ion difference, then we need to appreciate that from an electrolyte point of view, the big electrolytes that are really the role players here are sodium and chloride and any other strong anions. So the strong ion difference helps us explain normal anion gap acidosis, and in a normal anion gap acidosis, when we calculate that anion gap, what's happening in reality is that the change in bicarb and the change in chloride are offset against one another. The strong ion difference can also be used to explain raised gap acidoses, and our things like lactate and ketones, etc., are other strong anions which change the strong ion difference dramatically. So the presence of these other strong anions then would be included in this calculation of strong ion difference. So again, if we look at what a normal strong ion difference is, it's approximately 35 millimoles. So if we take a normal sodium at about 145 and a normal chloride at around 110, the difference between the two is about 35. And any change in the strong ion difference is roughly equivalent to the change in the base excess or the standard base excess. So to give you examples of this, if we had an electrolyte abnormality where the strong ion difference were increased to 45 millimoles per liter, then the base excess or the standard base excess would be positive by about 10 millimoles per liter. Similarly, if the strong ion difference decreased to 25, then the base excess or the standard base excess would be about minus 10 millimoles per liter. And then last of all is just to say a little bit about ATOT. So this is the total amount of weak non-volatile acid. Obviously, when we consider acids in this context, CO2, which is the biggest contributor, is volatile acid. We can breathe it out. And non-volatile acid then really includes proteins and phosphate. And again, if we think about the total or all of ATOT, the amount of variation we see in phosphate is relatively small and would not account for any big acid-base disturbance, but albumins can change fairly substantially, particularly in the setting of critical illness. And I think the important thing to appreciate here is that protein and phosphate are both significant buffers. And clearly, although we measure a small concentration of phosphate in the plasma, the intracellular and total body content of phosphate is high. And then last of all is just to say that albumin is a weak acid, and the implication of this then is that a low albumin would tend to have an alkalinizing effect, or would tend to have the effect of pushing the pH up, which is a particularly useful thing in the setting of critical illness. So if we go back to question 4 then, so this is really where we saw a metabolic acidosis with a base excess that was minus 18, and as indicated in the slides before, this would be associated with a low strong iron difference. The fifth question that I've put together for you is a 25-year-old HIV positive patient presents feeling generally unwell. The patient's ARV regimen has included stavudine, and the patient has a respiratory rate of 25. The patient's been receiving therapy with normal saline, and if we have a look at the blood gas, then the blood gas looks as follows. So the pH is 7.3, the CO2 is 4 kilopascals, the base excess is minus 10, the sodium is 130, and the chloride is 105. And the questions are, which of the following is correct? This could be a fully compensated respiratory alkalosis. The strong iron difference is low, which will tend to raise the pH. The anion gap could be normal, despite a low strong iron difference. A low albumin may contribute to a metabolic acidosis. So if we go through these, really the devil's in the detail. Were this to be a compensated respiratory alkalosis, the pH would not be low. Bear in mind, if the primary disorder was a respiratory alkalosis, so a pH above 7.44, then we couldn't compensate ourselves back into a normal range, and this patient in fact had a low pH. This must be a metabolic acidosis, but obviously the big question is, what is its cause? And in the little clinical vignette, we've got an HIV positive patient who's on stavudine, a drug that's known to be associated with acidosis. The patient has also had therapy with normal saline, so we could have a hypochloremic acidosis. And so, although this is a metabolic acidosis, teasing out the cause would take a little more detail. It could be lactate from the patient becoming dehydrated and shocked, but we would need to know what the anion gap and perhaps what the strong iron difference is. It could be long-standing diarrhea associated with a normal anion gap and a small strong iron difference. So we would have to tease our way through these various options. Just remember, importantly, that a low strong iron difference is associated with acidosis, and a high strong iron difference is associated with alkalosis. And to try and help you remember the difference between the two, you can think about why it is that the administration of Sodabic raises the pH. The traditional acid-base thinking would be, well, when we give Sodabic, we give bicarbonate, and that pushes the pH up. But clearly, when we administer Sodabic, we give a big load of sodium, and hypernatremia is one of the consequences, and so Sodabic pushes the strong iron difference up. And then last of all, in the previous question, we commented on the fact that a fall in albumin would produce an alkalosis. So clearly, in terms of the last option with this MCQ, that wouldn't have been appropriate. So if we have a look then at the right answer here, then the right answer would be that the anion gap could be normal despite a low strong iron difference. So that would be a a low strong iron difference acidosis, normal anion gap. And then the last question that I've put together for you is a teenager presents to casualty after being at a party with friends. The patient appears to be intoxicated and the GCS is very low. And the blood gas is as follows. So here we see the patient has a pH of 6.9, so clearly very, very acidotic. The CO2 is 6.9 kilopascals, so that's elevated, and there must be a component of a respiratory acidosis. But we look at the standard base excess, that's minus 20, so there's also a very significant metabolic acidosis here. So this is in all likelihood a mixed respiratory metabolic acidosis. And then we see that the lactate is 38. And the questions here are which of the following is correct. Hypoventilation likely accounts for this severe respiratory acidosis. This is just a profound lactic acidosis. Either the blood gas analyzer is faulty or there's another error, or this is most likely a case of ethylene glycol poisoning. So if we have a look at this scenario, there's a dilemma that exists in the results we presented with. The patient has a very severe acidosis, and this is a combined respiratory and metabolic acidosis. But the elevation in the lactate is not seen in the base excess. So if we have a look at the lactate here, the lactate's 38, and that increase in lactate would alter the strong iron difference because, as I said to you previously, any change in strong iron difference would be mirrored in the base excess, and lactate's a strong anion. So if we look at a lactate of 38, we'd have to accept that's elevated by at least 36 millimoles from normal. And if we elevate the lactate by 36 millimoles, we should see a reduction in the strong iron difference by 36 millimoles. And we'd expect to see a reduction in the base excess then by 36. But here it's only 20. And so this abnormality there, or this incongruency, must attract our attention. And so the reality is this is most likely a cause of ethylene glycol poisoning. And unfortunately, the lactate electrodes on a number of blood gas analyzers will erroneously read ethylene glycol as lactate. And the big clue here is the amount that the blood gas analyzer thinks it's measuring in terms of lactate doesn't make sense in terms of the rest of the acid base. So there's clearly a problem. So to summarize and to end off then, when you're dealing with acid-base problems, try and approach them systematically. Look at what the pH is and decide, is this an acidemia or is this an alkalemia? And then look at the partial pressure of carbon dioxide and either the base excess or the standard base excess, and try and figure out which is the predominant abnormality creating the pH disturbance, and then also consider that you could have a combined disturbance, so more than one abnormality. Think about what your predictions are in terms of the rule of thumb that I explained to you. Does the amount of deviation of the pH from normal make sense in terms of what you're seeing from a PCO2 and a base excess perspective? Consider the anion gap in metabolic acidosis only, and think about its relevance. And then always consider the impact of strong iron difference and weak non-volatile acid in acid base. And that's it. Thank you very much for listening. I hope this has been useful to you.